Hello there, welcome back to the Differential Questions by Alexander. Okay, so today we're going to do a little bit of physics, and what we're going to do is we're going to talk about the vibration of a mass on a spring. And so our goal is going to be to translate some physics into the differential equation. We won't actually solve any differential equation, we're just going to do a little bit of math modeling, so from physics to ODEs. And then the situation is the following. Suppose that on the top we have the red ceiling, and on the ceiling we hang a spring, a coil spring. And then what we want to do is we want to put a mass on it, so a block of gold, let's say. And then once we put it onto the spring, hang it on the spring is going to be stretched by an amount. And so suppose that we also pull down on the gold block of mass and let it go, and then the mass is going to be going up and down, up and down. And so we want to know what is the behavior, or what are the how does the system vibrate as you let it go. So that is what we want to deal with. And you're probably thinking, why are we going to be dealing with this? So just in case you don't know, and then this is going to be my fancy car here at the very bottom. So not the best car, so very ugly car. And so what I want to say to you is that behind the wheels, you actually do have some springs. Usually you do have a spring coil, and you do have your tire attached to it on the front and possibly on the back, and depending on your suspension, depending on the year of the car also. And so those springs are what make your car comfortable to ride. Explanation here, but this is a very good example. And then depending on how good your model is, that's how well you can prepare your car to be a smooth ride. All right, so just a little explanation there. Okay, so in order to start our discussion, we need to talk about some physics laws. Okay, so we're going to translate physics to ODEs. And so the first physics law that we're going to deal with is going to be the Newton's law. And so just to get some notation done, M is going to be the mass of a body, which is the block of gold that I told you before. V is going to be the velocity of the body. So suppose we kind of like give a little velocity to the block of gold. Force is this is going to be the resulting force, and we'll talk about that later. And now C is the constant proportionality. And so when you have this, Newton's second law of motion can be written in this format. And in this format, we have that mass times velocity, which is the momentum. And so what this is telling us is that the time rate change of the momentum is proportional to the force. All right, so in words, that's what I'm saying here. So you can kind of pause and you can read the words, but the momentum is what we're focusing on this version of Newton's second law. So probably not familiar, and so that's why I have this extra question here at the very bottom. If m is a constant and c is equal to the number 1, so this is the number 1, and if m is a constant, you can actually take this outside the derivative, and in that case you will have m, the time derivative of the velocity, is equal to the force. But now what is the time derivative of velocity? Well, then that is going to be the acceleration, which is the version that you kind of have seen before, and we usually write it out the other way, but just know that you can always write it the other way. So that is the Newton's second law of motion. And now the other law that we want to take, that we are going to use to be able to describe the spring mass system, we also need to talk about the Hooke's law, which is related to the spring behavior. Okay. All right. So notation again, F, this is going to be the magnitude of the force, S is going to be the amount of elongation, K is the spring constant of proportionality, and let's go back to the S. Okay, so what this means is the following. So you have the ceiling again, and on the ceiling you have this this coil spring, and then that's the coil spring just hanging there, not doing anything to it. And then we said that we are going to attach a gold piece of block, a block of gold, and when we do that, the spring is going to be stretched by an amount. And so what we're saying is this: the original position of this black spring is my first gray dotted line, and my second gray dotted line, that is my new position where it is in equilibrium. The spring and the gold block, they are in equilibrium, it's not moving. And so this is what we mean by S, the distance that the string has stretched in order to hold the block of gold. So that's what S refers. Elongation, or you can say stretching. Okay, so that's another way to say the same thing. All right, so now the Hooke's law says the following. Hooke's law says that the force is proportional to the amount of stretching, but now here we have to be a little bit careful on two things. Okay, so but before I do that, let me just give you the words here. The magnitude of the force needed to produce a certain elongation or stretching of the spring is directly proportional to the amount of the elongation. So that's in words, and I do have an example here to kind of make sense of this. But before we go on, there's two things that I want to say. First of all, since this is a physical model, or we're trying to model this physically, we have to make a little bit of here of a footnote, and the elongation or the stretching is not too great. Okay, so this only works if the stretching is not too much. If you stretch the spring by a whole lot, then you probably most likely will break the spring, and so all the physics that you deal with doesn't work. All right, the other thing that I want to mention here is related to the Hooke's law is the following. We want to be careful on who is doing the force to. Okay, so the mass on the spring produces this force. Okay, so this is the mass on the spring produces F is equal to Ks. That's the force. Now the other way around is the following. The spring on the mass, okay, produces the restoring force. So this is what we call the restoring force, and F is equal to negative Ks. So there's a negative sign. So just make sure that you are careful on who is doing the force onto. Okay, so the spring on the mass, you have the extra negative sign. All right, so now just to give you a little example, question number 1 says, suppose that you have a 30-pound weight stretches a spring by 2 feet. And now we want to use Hooke's law to find the spring constant of proportionality, okay? And so this is the mass doing a force onto the spring. And so the law that we're going to use is the following. This is the force that the weight does to the mass does to the spring. And so the force is given by this 30-pound. Weight is actually a force, the force due to gravity. And so this is the 30. And then we have the stretching amount to be a 2 feet. So that means that the K is equal to 15. All right, so that's how you find your constant of proportionality in this specific example. Just give you a little bit of exercise here. All right, so it's a lot of words here next, but before reading that, I'm going to draw the picture, and as I draw the picture, I'll go line by line, okay? So first of all, let's put in our picture that we had before, where we had the ceiling. The red part is the ceiling, and on the ceiling, we have a spring that we attach to it, and there's a loose end at the bottom. And then what we're going to do is, before we move on, I want to say that the first item says, a coil spring has natural length L. And what that means is that the length of the original spring, without doing anything to it or putting anything on it, the natural length is L. So that's the length of the spring, the natural length of the spring, L. So now, second item says a mass M is attached at the lower end. And so that is my little gold block, or my block of gold, I should say. And then when I put the gold block onto the black spring, it's going to stretch by an amount, and so I'm going to denote that by my gray line. So my gray is supposed to be my spring that has been stretched so that it is now holding the gold block. And so once it is in equilibrium, the spring is stretched by an amount of S, and then so this is extra amount is given by S. This extra amount that the black spring is stretched to get the gray spring, that is the S amounts. Okay, and so what that means is the following. We also have another piece of information here. We are saying that the spring mass, so the spring together with the mass, has a total length of L plus S, which is from the combining the two things. So L plus S is the combined length of the spring together with the mass. They are now in equilibrium, and then that distance that is in equilibrium is L plus S. So now, to be able to describe the system a little bit more precise, we need to put an axis on this. Okay, so we're going to put a vertical axis through the picture. So where the blue vertical line is supposed to be just an axis. Okay, so we're not doing anything physically. We're just now turning this into the mathematical situation. We want to situate ourselves in the picture. And so what we're saying is this: the location where the mass is, the mass that is attached to the spring, that is going to be my zero location, okay? That is going to be my zero location. And going up is actually going to be my negative x direction. Going down is actually going to be my negative x, my positive x direction. So it seems a little backwards, but that's usually how the modeling goes for this type of problem. So that's my blue axis. The center, which is where the gold block is, that is my center, which I call 0 location on my x-axis. And then going down, that is actually going down on the positive x-axis. Going up on the picture, that is actually going in the negative x direction. And so that's what I have said on the next two bullets here. So yeah, so that's what that says. And actually, I've already covered the last topic already also. So x equal to 0 means that you are at the center of your axis. If you let x be positive, then you actually are below the 0 location. Okay? If x is positive, then you actually are below the 0 location. And if x is negative, then you actually are above the 0 location on my blue axis. So that's our way to make this a little bit more mathematical. So we have the spring together with the mass. It's an equilibrium, and now we want to say something mathematically about the system. But before we do that, we need to put an axis. We need to locate our 0 location, and then we need to say which way is positive and which way is negative. All right, so now that we have this setup, we translated a little bit of the physics into the mathematical setting. Now we can continue with the physics, and then we want to say the following. If we have some forces acting on the spring mass system, what is the equation of motion? Meaning, what is the function? So this is going to be a function of time, and then this is going to tell us the location on the x-axis. So where on the x-axis is your block of mass moving? Okay, so it's going to be moving up and down, and then you want to know where is the gold block of mass on the x-axis as time progresses. And so we are looking for a function x that tells us what is the x position as, for whatever the time is. All right, so before we do that, we actually need to come up with a differential equation that kind of describes the physical situation. Okay, so this is actually the answer to a differential equation. And now what we're going to do is we're going to set up the differential equation. All right, so now this is where we have to talk about the forces acting on the system. Okay, so the first force is going to be the force of gravity. So that refers to the mass. Okay, so force of gravity refers to the mass, which is going to be mass times gravity. Okay, so that's the simple force. Now the second type of force is called the restoring force. So this is actually related to the spring. Remember, this is the force that the spring does to the mass. Okay, restoring force is the force that the spring does to the mass. And so here we do have to be a little bit careful with our notation. Let me just go back one slide because I need a little bit more space. And what I need to do here is the following. So I'll draw my ceiling, and then I'll write down my black my black coil spring. And what we're saying is the following. I'm going to attach a gold block to the spring. It's going to be stretched by a certain amount. Okay, so let me just draw that in gray like I did before. But what we're saying now is that suppose that we stretch it out by even a further amount. Okay, suppose that we stretch it out by a further amount, and so that means that the spring has stretched even further. Okay, so that's my purple line, and so what we're saying is that the original amount of length of the spring was L. Then we have stretched it by an amount of S. And then remember that this is the 0 location on my positive x-axis. So let me just write it out here. So this is the 0 location on my positive x-axis. And then now I'm going to stretch this by an amount of x. Okay. So how much have I stretched the original black spring? How much have I stretched the original black spring? So I have stretched that by an amount of S plus X. Okay. So now this is where the Hooke's law comes in. And so the amount S plus X is what we have stretched the original black spring. And so by Hooke's law, we know that the magnitude is going to be Ks plus X. But now there is a little bit of catch here. Remember that I told you that we need to be careful who is doing the force. This is the spring acting on the mass. Okay, and so that's why we have to use this version of the Hooke's law where we have a negative sign. All right, so before we do anything else, I just want to emphasize that we want to simplify this a little bit. And so I'm going to distribute, and then what I want to say is the following. We want to get rid of this parameter s because we want to model the situation, but if we introduce a whole bunch of parameters and it gets very complicated to work with, and so we're trying to eliminate whatever we can. And so in this problem, we are going to be able to eliminate the s in the following way. Okay. So when the mass is in equilibrium, the force, this is the opposite of the weight. Okay, and so the opposite of the weight, that force is going to be equal to negative ks, which is the force that the spring does on the mass. And so when you simplify this, then you get this equation. And what that is telling us is that you can replace the ks by this mg. Remember that the F2, we have rewritten it so that we distribute the K, and we are going to now replace the Ks with a Kx. Okay, so I flip up things here. Okay, so I'm supposed to, okay, so if you kind of bear with me here, I flip these two things, but all I'm doing is just replacing the Ks with the Mg. That's all I'm doing. And so what I'm saying here is that this is my F2 force. Okay, my F2 force is given by negative Kx minus Mg, and F2 is related to, it is my spring restoring force. So this is the force related to the spring, that the spring does. All right, so now another force that we want to take care of is the following. So suppose that you have a beaker, okay, so you have a beaker like in science class, and then you fill it up with some fluid, and then for some reason you have this, you have a red top to it, and on that red top you attach a spring, and then attached to that spring is a gold block. And now you pull down on the gold block, and then you let it go, and then you want to know how the spring mass oscillates or vibrates inside this beaker that is filled with some fluids. And so the fluid is going to be giving a force to the system, and so that's what we call a damping force. Okay, so this is one type of a system where the spring mass is immersed in a fluid. Now there is another type of damping force, which might be a little bit more familiar to you if you know a little bit of car mechanics, and that's going to be the following. So let's just draw a very simple car. Okay, so very ugly car. You have the two tires here, not the best car, but what I'm trying to say here is the following. Behind the car, you do have and I'm going to draw this in blue just to kind of show you the spring. There is a spring that kind of helps the suspension, but next to the spring, there usually is also a thing that looks like a tube, but this tube is allowed to get bigger or smaller, and that is in mechanics, car mechanics, is called a shock absorber. In physics, it's called a damper. Okay, a damper. So that actually is the proper name, damper, but most people call it a shock absorber. And so what we're saying is this: the spring, together with this shock absorber or damper, that helps your suspension, but that damper is what causes a damping force. Okay, it causes a damping force. All right, so that's a little bit of car mechanics here, and a little bit of fluid mechanics. And so now with this information, I want to go to my formula, and I guess that's my damping force. And now the formula that I want to present is the following. So for small velocities, so this only works for small velocities. We're going to assume that the damping force is proportional to the velocity. The damping force is proportional to the velocity of the motion. Okay, and beta is a positive number, and that's going to be called the damping constant. But now the damping force is going to be acting on the opposite direction of the motion, and so that's what I'm saying here. And then that means that we are going to put a negative sign to the formula. Okay, so the damping force is negative beta, which is a positive number, times the velocity. So opposite the motion. All right, so that's the damping force. That's the third force. And now the last type of force is actually a collection of forces. You are going to have external forces, or called the resultant external forces, and it could be other type of forces. And I won't mention any specific ones. Let's just make it more general. And so anything else is going to be labeled as F4. F4 is the external forces, or actually the sum of the external forces. All right, so now those are the four type of forces that are going to be acting on our system. And again, the first one is related to the mass of the system, the weight. The second one is related to the restoring force of the spring. The third one is related to the damping force, or actually is the damping force. And then number four is all the other forces, the resulting forces, external forces. And so now we're going to use the Newton's law of motion, which says F is equal to ma. We're going to write it in this way: ma is equal to F, and a is the acceleration. And since the x refers to the position of our mass of our gold block, the acceleration is given by x double prime. And now this is going to be the sum of the forces that we talked about in the very top. And what we're going to do is we're going to replace them into the formula, and then we're going to simplify them. So we're going to have mx double prime, this is going to be equal to F1 is mg, F2 is negative kx minus mg, the F3 is negative beta x prime, and then the last one is plus f of t. So now what cancels out? Notice that the mg cancels out, and so we get that the mg minus mg, they go away. And now I'm going to move a few things here and there, and so the equation that we get is mx double prime plus beta x prime plus kx is equal to f of t. All right, so the equation on the very bottom, that is my differential equation that is going to describe, that does describe the motion of the spring mass system. All right, so if I am able to solve the differential equation, then the function x that satisfies the differential equation with some initial conditions, then that function is going to describe to me, is going to tell me, hey, this is how the spring mass moves up and down. Okay? But today we are only coming up with the differential equation, and notice that this is a second order linear differential equation where the constants are m for mass, beta for the damping force, k for the spring constant, and capital F for the external forces. All right, so now given that we do have this, I want to say that instead of dealing with the general case, we're going to break it up into three little cases, okay? So well, step by step, kind of get complicated. The first case is the easiest case, where it's free refers to the F is equal to 0. Undamped refers to the beta is equal to 0. So we have the general equation on the very bottom, and we made the beta equal to 0, and we made the F equal to 0, and so that's how we get this first simple case. And then we call this the harmonic motion. Okay, because it's very, actually this is a very important topic here, and so we want to focus on this on the next video. And then the next video after that, we're going to talk about the free, which again, this is F is equal to 0, but the damp is damped, and so there is a beta, as you can see in the formula. And then on the next video, so three videos from now, we're going to be dealing with the full example, or the full equation. And so that's how we go from physics to the differential equations. We go into the topic of second order linear differential equations. Right, so that's a little bit of physics, a little bit of translating the physical situation into the mathematical model, and then coming up with a differential equation. And now we are in the situation that we have dealt with in the previous chapters, and so now we want to solve this, but because it is a physics problem, there is a little bit more to say to the solution of the differential equation. So we know how to solve it, but there is a little bit more to say physically, and so that's what I want to focus on in three different cases, because there's a lot of topics in there that we want to say that are related to real life applications. All right, so I hope that this is helpful, and I hope that you continue watching, and I'll see you next time. Thank you for